Determining causation is a central part of science. The problem is that we always start with a pattern, such as a cluster of extinctions associated with ejecta from a meteorite strike. But then we try to come up with a causal explanation, such as that the impact event caused the extinctions. This leap from pattern to process is the central problem of science. How do we infer cause from effect? All science deals with this problem, whether you're a paleontologist or an epidemiologist. In historical science, we typically solve this problem by identifying a series of correlated events or phenomena. We then do experimentation on modern systems or computer models to figure out how correlated events can produce a pattern in the fossil record. Alternatively, we make arguments based on probability, such as that impact events are rare, so a big one associated with extinctions suggests cause and effect. Still, another line of argument might be that we know impacts do all kinds of horrible things, so surely one or more of them is the cause behind the extinction. Looking at the history of extinctions, we have background extinctions that happen all the time, and mass extinctions that happen rarely. The latter include the Big Five of the Phanerozoic: the end Ordovician mass extinction at 440 million years, más o menos, the end Devonian about 360, the Permo-Triassic mass extinction, pretty well dated at 251 million years ago, the end Triassic at 201, and the Cretaceous-Paleogene, or KPG, event at 66 million years ago. Some of these are very big. For instance, the Permo-Triassic event resulted in an estimated loss of 96% of all marine species. This estimate comes from the average number of species in a given taxonomic family. We know the family-level extinction pretty well, so we can make an estimate of the species-level extinction, even though we cannot count species very accurately. Today, we address what causes a mass extinction. For that matter, what causes background extinctions? In principle, extinction could be due to extrinsic causes, that is, things which are causal mechanisms exterior to Earth, like asteroid impacts, solar flares, supernovae, and so forth. Alternatively, the causes may reflect intrinsic features of Earth's biosphere, such as ecological competition, disease, climate change, anoxia, volcanic eruptions, sea level fall, and supercontinent formation. There is also the problem that big extinctions almost certainly have multiple causes. Of course, really big events might still have a single proximate cause, such as a disaster like an asteroid impact or the Siberian traps erupting through coal beds. Alternatively, they may reflect multiple interacting causes that add up to a pattern not explained by any single phenomenon. To resolve the causes of mass extinction, we need a couple of pieces of information. First, we need high-quality timescales, and these have several components. For instance, it's critical to have good correlation between various records of an event that specify the pace and nature of environmental change and the extinctions that we're trying to explain. Correlation allows us to determine if the same events happen at multiple places on Earth at the same time. For instance, Snowball Earth models assume synchronous global glaciation. Such models would be in trouble if glaciation occurs at different times in different places. Another example is the global distribution of debris from a massive meteorite strike. This should also form a global deposit that can be evaluated as a singular instantaneous event. Second, we need relative time. Here the question is how closely a given event occurs in relationship to another possibly causal event. For example, how close is a mass extinction to the timing of the impact event? Third, we need a good handle on rates. The tectonic assembly of continents is probably not a good explanation for a sudden, nearly instantaneous extinction. After all, continental consolidation happens so slowly relative to extinction that it is reasonable to wonder how they could be related. Unfortunately, our resolution of time is often so poor in the fossil record that detecting the difference between events happening, say, in a day, like an impact event, versus over a few thousand years, or even 10 or 20,000 years, is oftentimes very hard. Also, our time resolution of events gets worse the farther back in time we go. The record of rapid events is often seen best in rapidly accumulating sediments, but these are often harder to study, since we may have to look through many thousands of meters of sediment for rare fossils to detect an extinction in the first place. So with those provisos, we can look at an example. Here we ask what caused the KPG boundary mass extinction at 66 million years ago. We have at least two competing theories. The first is that an extinction was triggered by a massive impact event. We know that an impact actually happened, and that it produced the Chicxulub impact structure in northern Mexico, a classic bolt from the blue event. The second model is a prolonged 700,000 year episode of volcanic eruptions. These also happened and are called the Deccan Traps of central India, a protracted event of climate change associated with massive flood basalt volcanism. If the impact is the cause, we expect most extinctions to cluster right around the impact horizon. Indeed, most of the end Cretaceous extinctions happen in an interval far less than 700,000 year long period of time suggested by the Deccan Traps. Deccan Traps supporters say that this happens because the eruptions were more voluminous and faster right near the extinction, and therefore more deadly. Deccan supporters also point to the dinosaur extinction and note that it appears to be highly protracted, with a gradual loss of dinosaur diversity in the last 10, million years or so of the Cretaceous. So this is the state of play. We have two catastrophic extinction mechanisms and a classic back and forth of evidence to support each. The obvious need is to refine our understanding of the pace of the extinction and its exact timing. One of the first things we notice is that the dinosaur fossil record is mainly that of very large animals, perhaps because these are easier to find and easier to preserve. Now, one way around this preservation snag is to greatly increase sampling effort for dinosaurs to get a true estimate of their actual abundance before the extinction. Some years ago, Peter Sheehan at the Milwaukee Public Museum did just that. He led a group of elder hostile volunteers to comb the hills of Montana below the impact ejecta bed. The impact layer had been found years earlier in the middle of a distinctive coal horizon called the Z coal. Sheehan found out that the highest occurrence of an articulated dinosaur was 3 meters below the impact level, which is probably at least a couple 100,000 years before the impact horizon. Above this, closer to the impact horizon, they found only bits of dinosaur bones. This sounds pretty promising for the notion that the impact occurred after the actual extinction, and therefore probably was not involved. But wait, more recently, David Festovsky at the University of Rhode Island led another massive group of volunteers, and this time they picked up and identified all those dinosaur bits below the Z coal. They found that most dinosaurs range right up to the impact level, but only as disarticulated bones. Their conclusion was that all dinosaurs present in the last several 100,000 years before the impact event made it up to the impact horizon. Big articulated fossils are so rare that you only see the true record if you look at dinosaur pieces. Note that if the problem is just finding enough fossils to define when the extinction happened, then we ought to do better with smaller-bodied creatures, since they are more abundant and therefore easier to sample accurately. So one solution is to look at really little things like foraminifera and nanofossils. In the case of foraminifera, a typical open ocean community had, say, 40 species in it in the late Cretaceous before the impact horizon. Of these, we find more than 50% of those species range right up to the impact level, and then either disappear or more commonly kind of dribble into the Paleocene sediments above the impact level and then disappear. Some species do vanish below the impact horizon, below the KPG boundary, but they disappear closer to the impact layer than the dinosaurs do. The basic pattern is that of changeover from Cretaceous to Paleogene species over like 50 centimeters to a meter of section in many cases, representing perhaps 30 to 70,000 years. The extinction looks pretty abrupt and is close to the impact horizon. Now, there are two ways of looking at this situation. First, the record can be read literally as evidence against a bolt from the blue causation, but more of an abrupt event for foraminifera than for dinosaurs. Alternatively, there is the possibility that the record is strongly affected by sampling effects that disappear or at least are minimized when you increase your sampling effort, either of dinosaurs or of foraminifera. As it happens, we can easily model this problem of sampling. What we find is that rare species tend to become extinct before common species in any given stratigraphic section and any particular kind of fossils. Rare species always appear to have a more gradual pattern of disappearance than more common things, simply because we are much more likely to find common species than rare ones. This pervasive pattern has been called the Signor-Lipps effect, after its describers, Phil Signer and Jerry Lipps. The bottom line is that dinosaurs are quite rare compared to foraminifera, so it's hardly a surprise that dinosaur extinction looks more protracted than that of the microfossils. Therefore, oceanic microfossils, by virtue of their abundance, give a better idea of the true timing of extinction than the dinosaurs do. The disappearance of most foraminifera very close to the impact ejecta horizon in deep-sea sediment comes as strong evidence that they are wiped out by this bolt from the blue event, namely the impact, rather than the protracted volcanism associated with Deccan Traps. The apparent gradual loss in dinosaurs, on the other hand, is just that, an apparent pattern that could well represent a sampling artifact, not a true pattern of gradual extinction. Now here it is important to state that just because the dinosaur pattern could reflect the impact event and a sampling problem, does not mean that it did. Dinosaurs might still be responding to a different process of extinction than foraminifera, we just can't tell definitively. But those elder Hoster volunteers of Sheehan and Fastovsky suggest that when you really jack up sampling, the dinosaurs also made it to the impact horizon and not above. Score 1 for the asteroid.